Welcome to this week's podcast, which is titled Quantum Field Theory and the Spiritual Dimension. In this one, we're really going to get into how science and religion relate to each other. And we see here a picture from Plato's Republic. On the right-hand side of the picture, we think we're the people that are out there on the beach, looking at the trees and the sky and the sun, when Plato said, no, reality is very different. It's what's on the left-hand side of the picture. And Plato's view of reality coincides very nicely with the latest discoveries in today's modern physics. And that's what we're going to consider in this podcast. We'll have 6 categories we're going to look at. One of them is Plato's cave and the nature of reality. We'll look at how particles and fields relate to each other. We'll understand how quantum particles are not the same as Newton's marbles. We'll also look at, so what are things made of, which indicates the end of scientific reductionism. And then I'm going to attempt to explain quantum field theory. And we'll finish up with finding out that empty space is not really empty space. It's full of fields. Now, one example of the remarkable similarity between the findings of science and the findings of religion is that both reveal that matter is not what it seems. Many religious traditions hold that matter is an illusion. This is especially true in Hinduism, Buddhism, Jainism, and Sikhism. These religions embrace the concept of Maya, the veil of illusion cast over sensory perception. Yet the findings of science concur that matter is nothing like what our senses reveal. In fact, most of reality is hidden from our senses. The primary difference between the science of religion and the science of the material is in the discovery process. The science of matter's view of reality is based on the repeatability and consistent findings of physical experiments, whereas most religion's view of reality is based on the repeatable and consistent findings of the transcendent experience of the mind. Quantum mechanics is based on a clear mathematical apparatus. It has enormous significance for the natural sciences, and it enjoys phenomenal predictive success. Yet, nearly 100 years after the theory's development, there is still no consensus in the scientific community regarding the interpretation of the theory's fundamental building blocks. Despite its undeniable success, the development of the equations of quantum mechanics only made it unnecessary to answer the deeper questions about the nature of reality. Physicists have gone on to prove, thousands of times, that until measured by an intelligent observer, everything, whether energy such as light or matter such as atoms, behave in a wave-like manner until measured by an intelligent observer. The inescapable conclusion, an intelligent observer plays an essential role in the formation of matter. One of the most important physics theories to be developed over the past 60 years is quantum field theory. Quantum field theory is a reformulation of quantum mechanics, and it calculates the exact same numbers as quantum mechanics, but quantum field theory suggests that the reality we experience is an illusion of the human senses. We think we live in a world dominated by matter. Why? That's the sound of me rapping on the table that's right in front of me. We run into matter all the time because our 5 human senses evolved to detect the world of matter. Our senses are relatively blind to the detection of fields. Therefore, we are biased in thinking that matter is primary and fields are secondary. Quantum field theory is earth-shaking in that it says that fields are the basic building blocks of the entire universe, while matter is secondary and totally derived from fields. This literally means that the matter our senses detect is an illusion and is not the true nature of reality. The philosopher Plato seems to have realized intuitively that the world of matter was an illusion long before quantum field theory made the discovery. It can be seen in his allegory of the cave presented in his work, The Republic, written between 520 BCE and 515 BCE. In Plato's Republic, Socrates describes a group of people who have lived chained to a wall of a cave all their lives, facing a blank wall. The people watch shadows projected on the wall from objects passing in front of a fire behind them, and they give names to these shadows. They think the shadows are matter. The illusion of the shadows on the wall are the people's total reality, but they are not accurate representations of the real world. Socrates then goes on to explain how the philosopher is like a prisoner who is freed from the cave and comes to understand that the shadows on the wall are actually not reality at all. A spiritual individual aims to understand and perceive the higher level of reality through the mind and not through the senses. In the world of matter, we literally live and breathe particles. Particles are localized entities that can have both a location and motion. In the physical sciences, a particle is a small localized object to which can be ascribed certain physical or chemical properties such as volume, density, or mass. They vary greatly in size or quantity, from subatomic particles like the electron to microscopic particles like atoms and molecules, to macroscopic particles like powders and other granular materials. Particles are the foundation of materialism. Here in this picture, you can see particles, which could represent molecules. They look like little round marbles. In a solid, they're packed closely together. In a liquid, they're spaced further apart and move around. And in a gas, they're even further apart and move probably faster. Fields are fundamentally different than particles. They do not consist of a point location, but are spread out through space, literally all of space, the entire universe. In physics, a field means that a physical quantity is assigned to every point in the space. In this case, space-time. A field is seen as extending throughout a large region of space so that it influences everything. The strength of a field usually varies over the region. A field is something that has a value at every point in space. It is non-localized. For example, if you consider the surface of a body of water, at each point the water has some temperature. So you could call the temperature field the temperature at each point in the water. Fields have motion, but it is very different from particle motion. What you're looking at in the picture here is an example of a type of field. It's an electric field. An electric field is the physical field that surrounds electrically charged particles and exerts force on all other charged particles in the field, either attracting or repelling them. It also refers to the physical field for a system of charged particles. Electric fields originate from electric charges or from time-varying magnetic fields. Electric fields and magnetic fields are both manifestations of the electromagnetic force. We've now come to a crucially important fact. Quantum particles are not the same as Newton's marbles. They don't act like Newton's marbles, and they don't obey the laws of Newton. Our confusion actually begins early in life, usually in middle school, where students are taught the concept of the atom as you see in the picture here. They even make models of atoms using foam balls for protons, neutrons, and electrons. This usually results in people thinking that atomic particles are just very tiny marble-like objects. The picture you're looking at here is not what an atom looks like. As a matter of fact, it's a physical impossibility. This common diagram of an atom still is taught in schools today, and we're lying to our students. It has been known to be factually incorrect since around 1906. The idea of a Newtonian marble-like particle fails when you get down to conceptualizing an atom. And here's why. First, the spacing of electrons from the nucleus is distorted in the atom above. In all the space between the nucleus of the atom and its orbiting electrons were removed, our body would be reduced to less than the size of a pinhead. Our bodies consist nearly entirely of empty space, as in 99.9999% empty space. Matter in its entirety is mostly empty space. Second, electrons do not orbit the nucleus like planets around the sun. If the electron were a particle with a negative charge orbiting the atomic nucleus, the atom would be totally unstable, rapidly so. A moving charged particle emits radio waves, a form of energy. Thus, the electron would lose energy as it orbits and eventually spiral into the nucleus. This would also mean that all matter would emit radio waves, which matter certainly does not. Electrons move at the speed of light, and as such, the electron effectively creates a permanent shell of energy around the nucleus. Larger atoms, with their greater number of protons and a correspondingly greater number of electrons, create what is often described as an electron cloud around the nucleus. If we were inside a small spacecraft and somehow able to shrink it down to the size of a neutron, and then try to fly inside an atom, we would be unable to penetrate the force field of energy created by the cloud of electrons around the nucleus. When an atom surrounded by its electron force field comes in contact with another atom's electron force field, a number of things can happen. They can bounce off each other and go their merry ways, or one atom can take electrons from or give electrons to the other atom in a process that changes both atoms. Or they can share electrons, a sharing that effectively glues them together. One thing, however, that the electron shells don't do in ordinary conditions is collapse. The electron force field is immensely strong. It is this force field-like electron cloud around every atom that keeps our mostly full of space body from meshing into our mostly full of space objects or from sinking into the ground on which we stand. The picture you're looking at here is a representation of the electron force field surrounding a single hydrogen atom with one electron. As you can see, one electron gives rise to many, many different shaped force fields around the single proton of hydrogen. Which brings me to my third point. Like the force field electron shells of constantly moving energy that surrounds the protons and neutrons of the nucleus, protons and neutrons are also composed of energy moving at the speed of light. So much for little tiny marbles. The nucleus of the atom was actually a super condensed, super high frequency form of energy. The famous equation E equals mc squared proved that there are no undividable, super tiny little balls of solidity. The absence of solid matter at the core of the atom, and also of the electron, has since been proven over and over again particle accelerator experiments. So as you can see, the world of little tiny marble-like atoms that move according to the laws of Newton's is basically an illusion. So, if you happen to be a high school physics teacher, you have the unenviable task of having to have all of your students unlearn everything they were taught in elementary school about what atoms are. No more styrofoam models. It's all basically a lie. So here's a hypothetical conversation you can have with your 5-year-old child who wants to be a scientist. They'll ask the question, what are people made of? Well, people are made of muscles, bones, and organs. Well, what are organs made of? Organs are made of cells. What are cells made of? Cells are made of organelles. What are organelles made of? Organelles are made of proteins. What are proteins made of? Proteins are made of amino acids. What are amino acids made of? Amino acids are made of atoms. What are atoms made of? Atoms are made of protons, neutrons, and electrons. What are electrons made of? Electrons are made from the electron field. What is the electron field made of? At this point, there's dead silence because we don't know. And sadly, here the game of questions must come to an end 9 levels down. There is a hard limit to our scientific understanding. To the best of our present ability to perceive and to reason, the universe is made from fields and nothing else. And these fields are not made from any smaller components. A field can be spread out through the entire known universe. Starting to sound kind of spiritual, don't you think? We've now gone from the world of matter into, at the fundamental heart of everything, is the world of the spiritual. This was summarized by the Nobel laureate, Dr. Wilczek, who won the Nobel Prize and is one of the contributors to quantum field theory. And he states, and I quote, "The core theory which summarizes our best current understanding of fundamental processes is formulated in terms of quantum fields. Particles appear as secondary consequences. They are localized disturbances in the primary entities, and the primary entities are quantum fields." Now that we've discovered that matter is really a consequence of fields, and fields are really not detectable to our human senses, we now have a way of conceptualizing how spirituality can integrate with science, because we can now have mind fields, literally, that's mind, M-I-N-D fields, that can interact with an electron field or any of the other types of matter fields. All the things that we call particles have fields associated with them. And we can now start to think of how the universe can combine together to give us what we would term spiritual interactions, as well as they can manifest as physical interactions. It's not quite right to say that fields are the most fundamental thing that we know of in nature, because we know of something that is in some sense even more basic. We know the rules that these fields have to obey. So now we're starting to talk about rules being at the same level of consequence as matter. Our understanding of how to codify these rules came from a series of truly great triumphs in modern physics, and the greatest of these triumphs is quantum mechanics. I'm going to now try and explain what a quantum field is, and regrettably I'm going to have to stoop to using a physical example. Much like the atom that we make models of, I'm going to give you a material example to try and demonstrate what a field is. Realizing, in fact, that the little ball on a string that I'm going to talk about is not really what a field is created with. It is simply a metaphor that I'm going to use to describe and allow you to visualize field oscillations. So what we have here, a ball on a spring. This is an object from which our quantum field will be constructed. Specifically, this field will be composed of an infinite space-filling array of these balls on springs that you're going to be looking at the picture here. And it looks kind of like a mattress. You can think of it as maybe the springs in your mattress. So to keep things simple, let's suppose that for some reason, all the springs are constrained to bob only up and down. There's no twisting or bending side to side. In this case, the array of springs can be called, using the jargon of physics, a scalar field. A scalar field is a field whose value at a particular point in space and time is characterized only by a single number. In other words, what is the height of the ball on the spring? Now, in order to make this array into a quantum field, one needs to introduce some kind of coupling between the balls and the springs. So let's imagine adding a little elastic band, which are the red lines in the picture you're looking at. Let's add these little elastic bands between the spring ball array so that it resembles, again, a mattress. Now we have something that we can legitimately call a field. If you disturb this field, say by tapping on it at a particular location, then it will set off a wave of ball and spring oscillations that can propagate across the field. These waves are, in fact, the particles of the field theory. In other words, when we say that there is a particle in a field, we mean that there is a wave of oscillations propagating across it. For the present pictorial discussion, all you really need to know is that a quantum ball on a string has two rules it must follow. It can never stop moving, but instead must be in a constant state of bobbing up and down, always. It never rests. Number two, the amplitude of the bobbing motion can only take certain discrete values. The quantization of the ball's oscillation up and down has two important consequences. If you want to put energy into the field, in other words, this is my saying that we're tapping the field using our little mattress metaphor here. So if you want to put energy into a field, you must put in at least one quantum. In other words, these balls can only bob up and down in discrete energy units. You must give the field enough energy to kick at least one of the ball and springs into a higher energy state. The field will simply not react to energies below a certain threshold of one quantum. Once you tap the field hard enough, however, a particle is created, and this particle can propagate stably through the field. The other big implication of imposing quantum rules on the ball and spring motion is that it changes pretty dramatically the meaning of empty space. So in this picture that you're looking at now, we've turned our ball and spring mattress into a grid-like depiction where you see horizontal and vertical lines that intersect. The intersection of these red lines in the lower matrix is where you would find one of the balls and springs. We've now transformed it into something a little bit more realistic in that we're using the ball and spring metaphor to visualize this, but we've now converted it into a flat matrix. The red matrix, well, this figure shows in red the underlying excitation of the quantum field, which corresponds to the resultant particle. This is the red spot on the green plane above it, which appears when the field is observed. These particles, which are actually oscillations in the quantum field, have a number of properties that are probably familiar from the days when you just thought particles were little points whizzing through empty space. For one, they have a well-defined propagation velocity, which is related to the weight of each of the balls and the tightness of the springs and the elastic bands in our metaphor. This characteristic velocity is our analog of the speed of light. The properties of these springs also define the way in which particles can interact with each other. If two particle waves run into each other, they can scatter off of each other in the same way that normal particles do. Third, the particles of our field clearly exhibit wave-particle duality in a way that is easy to see without any philosophical hand-wringing. That is, our particles by definition are waves, and they can do things like interfere with each other constructively and destructively, which we can see in something we'll talk about in the next podcast, which is the double slit experiment. So this quantum field theory now gives us the structure of what is physically happening in the universe is wave-like from fields, and it manifests in these particles, which are oscillations in the field. Now this gets us to our final point. Empty space is not really empty. It's full of fields. Normally, empty space, or a vacuum, is defined as the state where no particles are around. No particles around doesn't mean that there's not a field still there. It just means there's no excitation in the field. For a classical field, that would be the state where all the ball and springs are stationary and the field is flat. But in a quantum field, the ball and springs can never be stationary, as we've stated before. They are always moving, even when no one has added enough energy to the field to create a particle. There's still background movement. This means that what we call vacuum is really a noisy and densely energetic surface. The random motion, called vacuum fluctuations, has a number of fascinating and eminently noticeable inferences on the particles that propagates throughout the vacuum. So what does all this have to do with God and spirituality? The Jewish mystical practice of Kabbalah calls God the Ein Sof, the creative nothing from which the universe was created. The Ein Sof is the hidden God force, or we can maybe call it a field that creates and sustains the universe. We'll be talking a little bit more about this in our next podcast. I hope what we've done here is instructive. I hope I've managed to communicate some very complicated scientific physics reality to you and give you some idea of how the universe actually operates. So thank you again for listening, and we'll see you in our next podcast.